Hello and welcome to the video lecture on organic synthesis, where we are going to continue our discussion on the chemistry of the protecting groups. এর আগের ভিডিও লেকচারটাতে আমরা অ্যালকোহলের প্রোটেক্টিং গ্রুপস নিয়ে ডিসকাশন করেছিলাম। এবারে আমরা কার্বনিল গ্রুপের প্রোটেকশন নিয়ে কন্টেমপ্লেট করব। Carbonyl, being a very highly electrophilic group, is susceptible to nucleophilic addition. Therefore, you need to protect your carbonyl in a sequence of reactions where you are using nucleophiles, but you are desiring the reaction of the nucleophile at other part of the molecule, not on the carbonyl. Also, the alpha hydrogens of carbonyls are relatively acidic because of the electron withdrawing nature of the C double bonded O, and therefore they are prone to enolization or enolate formation under basic medium, and that can lead to undesirable side reactions such as combination of an electrophile with this oxygen if this is a hard electrophile, and combination of an electrophile with this carbon, alpha carbon, if this is a soft electrophile. So these sort of undesirable side reactions may happen. Therefore, for an organic synthetic chemist, protection of a carbonyl is a central requirement. তো কিভাবে প্রোটেক্ট করা যায়? কার্বনিলদের প্রোটেক্ট করার সবথেকে ইজি এবং সবথেকে পপুলার মেথড হচ্ছে তাদেরকে অ্যাসিটাল ফর্মে প্রোটেক্ট করো। অ্যাসিটালস মে বি লাইক অক্সোঅ্যাসিটালস বা ওও অ্যাসিটালস, যেখানে আমরা কার্বনিলকে একটা অ্যালকোহল দিয়ে ট্রিট করি এবং সেখানে একটা অ্যাসিড ক্যাটালিস্ট লাইক ব্রনস্টেড অর লুইস অ্যাসিড ক্যাটালিস্ট থাকে, and then under anhydrous alcohol medium we convert the C double bonded O into a corresponding acetal. The acetal protection can be done also by diols, can be also done by orthoester, etc. Water is a byproduct of this reaction, which is generally removed by azeotropic distillation. If the features of the acetalization is noted, then it is seen that the general order of the reactivity for various carbonyl groups are like this, where aldehyde is the most reactive, the least reactive is the alpha beta unsaturated carbonyl compound. This is a combination of both electronic as well as steric effect. As you go on increasing the steric around the carbonyl carbon, the nucleophilic attack of the alcohol that is required for the acetal formation becomes discouraged. At the same time, as you go on increasing the number of alkyl groups around this carbon, or you conjugate this carbonyl with a carbon-carbon double bond, the electrophilicity of this carbonyl also decreases. As a result, the acetal formation becomes less favorable. Generally, there is, entropic penalty that is associated when you are trying to acetylize a ketone. এখানে দুই ইকুইভ্যালেন্ট অ্যালকোহল লাগবে, তার মানে এখানে তিনটে রিঅ্যাক্ট্যান্ট মলিকিউল থেকে দুটো প্রোডাক্ট মলিকিউল তৈরি হচ্ছে, একটা অ্যাসিটাল প্লাস একটা ওয়াটার। সো দিস ইজ অ্যাসোসিয়েটেড উইথ an entropy loss. This can be minimized if you do your reaction with a diol. In that case, একটা কিটোন মলিকিউল আর একটা ডাইল মলিকিউল, সেখান থেকে আমরা একটা সাইক্লিক অ্যাসিটাল পাচ্ছি এবং একটা ওয়াটার মলিকিউল পাচ্ছি। সো এন্ট্রপিক পেনাল্টি কিছুটা কম লাগে। So these are the 1,3-dioxolane, the 5-membered cyclic acetal. This is the 1,3,1. These are the 1,2 cyclic acetals. So these are the 1,3-dioxolanes, and these are the 1,3-dioxanes. So these are, fairly robust towards hydrolysis compared to these acetals, যেখানে আমরা সেটা অ্যাসাইক্লিক অ্যালকোহল থেকে পেয়েছি। And when you have 1,3-dioxane, that is 6-membered cyclic acetals, they hydrolyze faster compared to 5-membered cyclic acetals, and that sometimes help us in sort of our protection strategies in multi-stage synthesis. Let us consider a few examples. Protection of a ketone in presence of a ester can be done. because esters are generally not acetalized under this reaction condition. They are very much less electrophilic compared to the ketone, and therefore this blue carbonyl can be protected in presence of this magenta colored carbonyl, which is a part of the ester group, and therefore you have this protected thing. You are using tosic acid as the catalyst. Also, toluene is used as a solvent. Heating is required, and azeotropic distillation and removal of water is also done. Here we have two carbonyls, one of which is conjugated with the carbon-carbon double bond, so less reactive. So you can protect the non-conjugated, more electrophilic carbonyl easily by using the acetal protection strategy. Here is a molecule which is known as 4-oxo isophorone. Two carbonyls are there. This carbonyl does not have any alpha alkyl groups. On the other hand, this magenta carbonyl has couple of methyls here, one methyl also here. Both being conjugated with carbon-carbon double bond, it is the steric factor which determines that which one is more electrophilic and which one reacts eventually. It is the blue carbonyl which gets acetalized because of less steric hindrance compared to the magenta one, jar alpha position alkyl group থাকার জন্য nucleophilic addition is sterically very unfavorable. So all these things you can do. So what sort of protections do the acetals offer? Acetals are generally very stable to even very strong aqueous bases. So base থাকলে তোমার alpha hydrogen abstraction হয়ে যাচ্ছিল, সেটা হওয়াটা relatively difficult এখানে because carbonyl is no longer there and acetal is stable in base. কার্বনিলের আরেকটা প্রবলেম হচ্ছে নিউক্লিওফিলিক রিডিউসিং এজেন্ট যদি লিথিয়াম অ্যালুমিনিয়াম হাইড্রাইড সোডিয়াম বোরোহাইড্রেট ইউজ করো তাহলে সেটা reduced হয়ে যেতে পারে, but acetals are stable, therefore you offer protection on that count as well. Organometallic reagents like RMGX, RLI, etc., they very happily add to your carbonyl group, but not on acetals, that therefore organometallic reagent এর হাত থেকে protection দেয়. Aldehydes have this unfortunate tendency of undergoing oxidation very easily, but acetals do not undergo oxidation. They resist oxidants under non-acidic condition. Because if you use say Jones oxidant, যেখানে sulfuric acid, water এবং chromium, high valent chromium use করা হয়, that reaction condition can cleave acetals, and if that happens then your acetal protection is useless. But in non-acidic condition where you are using an oxidant, the aldehydes may get reduced, but if you protect them in the form of acetal, they stay. Also, Birch reduction type condition like sodium or lithium in liquid ammonia, those reductions are valid for the carbonyl group, but when you have acetal, it is protected from the undesirable reductions as well. Oxoacetal there একটা example দেখা যায়, but how to deprotect? Obviously you know that acetals are unstable in aqueous acid, so you just treat it with aqueous acid, maybe heat a little bit, and then you get your carbonyl compound back. So একটা target molecule থেকে দেখা যায় যে কি করে এই acetal protection কাজ করে. Let's check out this one. If I consider this carbon-carbon triple bond as a functional group, then this is 1, 2, 3, 4, and 5. So it's a 1,5 bifunctional unit. I can disconnect right next to the alkyne carbon and put a negative charge here. That would mean that this is a D1 syntone, and this one becomes a A4 kind of thing. 1, 2, 3, 4, acceptor 4. This is a gamma bromoketone. Recall that we have done the retrosynthetic analysis and forward synthesis of this one previously. And this D1 synthone is accessible because you just need one butane, a terminal alkyne, and therefore you can deprotonate it with a suitable base and you have your D1. But the problem is elsewhere. With this strategy, you require the SN2 reaction to happen here, but this carbonyl group is also very electrophilic. As a result, if you add directly onto this electrophilic molecule, if you add the alkyne anion directly, then the alkynide will attack the carbonyl group and will form a tetrahedral intermediate, a propargyl alkoxide, something like a tertiary alkoxide. So you cannot possibly do this reaction and hope that this will work. So what to do? You need to protect this carbonyl so that the nucleophilic addition is suppressed. So protect as a acetal. Form a cyclic acetal with ethylene glycol using tosic acid as catalyst in toluene medium and by removing the water by azeotropic distillation. Then you do the desired SN2 reaction on this carbon using the alkyl ion sodium salt, and then you deprotect with H2O+. So this is protection, this is reaction, and this is deprotection. Obviously you have two steps which are diminishing the yield, but without the protection, and if you have the protection you must also have the protection, your reaction will not occur. Therefore cyclic acetals are therefore ideal to keep undesired nucleophilic addition from carbonyl group. They can stop this thing from happening. The next example is ethyl acetoacetate. You can protect the keto group of ethyl acetoacetate with a cyclic acetal. Obviously esters are less reactive, ketone will be protected. Now suppose you have been asked to synthesize this molecule from ethyl acetoacetate. So that will require formation of a tertiary alcohol on this site and no reaction at this site. Tertiary alcohol can be generated by reaction of excess Grignard reagent on ester, but the problem is if you add onto ethyl acetoacetate the phenyl magnesium bromide, two things may happen. The first thing is, which is more likely to happen, is the abstraction of these hydrogens which are acidic, and therefore you will get an enolate kind of thing. That is not what you are looking at or looking to do. Or even if the nucleophilic addition happens, it's not the ester that is going to be reacting, it is the carbonyl which will probably ketomethyl or the keto group that will react, and you will get this one which is a tertiary alcohol but not what you are looking to synthesize. Therefore you need to protect this ketomethyl group in the form of the cyclic acetal. Once you do that, you can add excess phenyl magnesium bromide and then you get your tertiary alcohol derivative. This could be the magnesium salt, this could be the magnesium salt, and when you work up, then it becomes the OH, this becomes carbonyl, and this is a tertiary alcohol with two phenyl rings that can stabilize a plaster here. So it will undergo a very facile E1 reaction to afford you the alpha beta unsaturated carbonyl that was your target molecule. If they have asked to synthesize 4-hydroxybutane 2-1, that was this molecule, from ethyl acetoacetate, clearly you need to reduce this ester functionality into CH2OH. But then the carbonyl group must be protected. Otherwise, if you add lithium aluminum hydrate to this, two things may happen. Again, either the deprotection, either the deprotonation of this acidic hydrogen giving rise to a lithium enolate, or reduction, preferential reduction of the keto group via addition of the hydride, but your ester is not getting reduced. Therefore you need to protect again in the form of say cyclic acetal, and then you treat it with H2O+, so you get 4-hydroxybutane 2. Hydrolytic cleavage we have already discussed of cyclic acetals, but if you need to do reactions in a non-hydrolytic condition, then the acetal formation should be carried out with special alcohols like 3-bromopropane 1,2-diol or 2,2,2-trichloroethanol. These things can be used when used for acetal protection. You can deprotect via a reductive workup with zinc, just as here you are seeing that it is giving rise to allyl alcohol and a zinc bromide kind of thing, and you have your ketone released in the reaction medium. But these are specialized techniques. I don't think that you would be required this type of deprotection reaction where a zinc induced beta elimination is doing the job. For your course, this H3O plus deprotection is, I think, sufficient. The second type of acetal that you can use is the sulfur based acetal, dithioacetals, SS acetals. Preparation will require reaction of a 1,2 dithiol or a 1,3 dithiol to give rise to 1,3 dithiolane or 1,3 dithione derivatives. Water is produced, but because they are more robust towards hydrolysis, generally this removal is not a problem, and these reactions are catalyzed by Lewis acid catalysts such as PF3, etc. Deprotection will require removal of sulfur, and therefore we need thiophilic groups such as mercury. This is conveniently done with HgCl2 in presence of calcium carbonate, and you have acetone, aqueous acetone, where you have this carbonyl forming. So here you have the acid that is being generated here is captured by either calcium carbonate or mercury oxide, etc. Obviously you need some water here, so that's basically aqueous acetone. And if you are trying to do this reaction without the toxic mercury group, then you can methylate these sulfurs by using excess methyl iodide and then carrying out the reaction in presence of calcium carbonate, water in acetonitrile solvent. So this time with mercury, this was getting removed in the form of, say, mercury sulfur complex, and this time the sulfurs will be methylated and it will be removed from the compound. Again, if they have asked you to synthesize this beta hydroxyketone starting from this 1,3-dicarbonyl, this 1,3-dicarbonyl you can access by Claisen, or this beta hydroxyketone you can go for a aldol type reaction, but this aldol reaction will be a little bit difficult because that will require enolate from acetone reacting with the benzophenone. Benzophenone does not have alpha hydrogens, but benzophenone is very less reactive due to the electronic and steric reasons offered by the two phenyl groups. Therefore, you need to use specific enol equivalent to achieve this transformation. But that is not the point here. তোমাকে বলেছে এই কম্পাউন্ডটা থেকে বানাতে, এই কম্পাউন্ডটা থেকে বানাতে বলেছে, সো দ্যাট উইল মিন যে আমার এই জায়গাটাতে নিউক্লিওফিলিক অ্যাডিশন লাগবে ফিনাইল ম্যাগনেসিয়াম ব্রোমাইড দিয়ে. প্রবলেম ইজ উই cannot hope to add any phenyl magnesium bromide here when this is present. This ketomethyl ketone is very much more reactive compared to the keto group of the benzoyl, because benzoyl carbonyl is like conjugated with the phenyl ring, and as a result, when you add any nucleophile, it is the ketomethyl carbonyl which undergoes the nucleophilic addition. So you have phenyl magnesium bromide reacting with the preferentially with the ketomethyl. What to do? Protect it. Protect it either in the form of dithioacetal done in presence of catalysts such as HCl and ZnCl2, and then do the Grignard reaction. Once you have your Grignard reaction, you have a magnesium alkoxide, and then you treat it with aqueous THF in presence of a mercury salt, and your deprotection is complete. Next up is the protection of amines. Amines have much less acidic hydrogen compared to alcohols. The alcohol pKa is like 15, 16, 17, that range. Amine pKa is like 35, so it's much less a problem. But if you add very strong nucleophile come base like magnesium, methyl magnesium bromide, or methyl iodide and methyl lithium, then you have deprotection. Generally, if this deprotection does not create a problem in the subsequent steps in the reaction, and you have excess Grignard reagent or organolithium reagent that you can sacrifice for this deprotection, in that case, this amine may not be protected. But generally, neither of this is true. You generally do not have organometallic or organolithium reagent plentiful. You don't have that. And secondly, when you have reacted this and this deprotonation has happened, it creates a problem downstream. তুমি যখন পরের স্টেপগুলো করবে সেখানে এই এন ম্যাগনেসিয় বা এন লিথিয় সল্টটা কিন্তু সমস্যা করে সাধারণত. Therefore, protection is required. More importantly, perhaps, because of the presence of the electron pair on nitrogen and because of its nucleophilic nature, it tends to react with electrophiles very efficiently and undergo undesirable reactions when this molecule is exposed to electrophilic reagents. Therefore, you need to, render this nitrogen lone pair as well as this NH2 group, less reactive. You have to make the lone pair less reactive, and therefore the amines can be converted to their amides. generally via acylation. For alcohols, we can think of in terms of ester formation. Here we are making amides in presence of say acetylation করতে গেলে অ্যাসিটিক অ্যানহাইড্রেট দিয়ে রিঅ্যাকশন করা যায় বা অ্যাসিটাইল ক্লোরাইড দিয়ে রিঅ্যাকশন করা যায় ইন প্রেজেন্স অফ আ বেস, সামথিং লাইক দ্যাট। অ্যান্ড অ্যামিনের একটা জিনিস মাথায় রাখা দরকার, সেটা হচ্ছে যেহেতু এটা হাইলি রিঅ্যাক্টিভ এবং ফ্রি অ্যামিনকে হ্যান্ডেল করা ডিফিকাল্ট, সেই জন্য আর্লি স্টেজ অফ দ্য সিনথেসিস যেখানে অ্যামিনটা অ্যাপিয়ার করলো তোমার মলিকিউলের মধ্যে, it is better to protect that amine at the very beginning and then carry out all the reactions on this R part, and at the very last possible stage you can deprotect the amine almost at the end of the sequence. You hold on to the protecting group as much as you can. Therefore amine protection is very very important, and the deprotection strategies are also very important, because if you want the protecting group to survive many reactions, you need a very robust protecting group which will offer protection from many different reagents. তো কিভাবে করা যায়? প্রথমত তুমি একটা বেনজাইল অ্যামিনের কথা ভাবতে পারো। n benzyl amine from primary and secondary amines, they undergo this type of benzylation reaction. When you treat that with PHCH2Br in say triethylamine and acetonitrile, or you can use sodium hydride in THF. So you have your either doubly benzylated or simply benzylated compound. So you know this hydrogen is gone, CH2PH ঢুকেছে, ফলে স্টেরিক হিন্ড্রেন্স বেড়েছে, etc. The removal is generally done with hydrogenolysis, with hydrogen in palladium charcoal or palladium acetic acid that regenerate the amine. Benzyl amines are not generally cleaved by Lewis acids. Then next protection is amide. Formation of say acetyl derivative with MeCOCl or acetic anhydride, you will generally need a base here to abstract the HCl or the acetic acid that is being generated. Otherwise your amine will get protonated and it will lose its nucleophilic activity, so acetylation will not be completed. If you have many vast quantity of amine that you can expend, then possibly you can avoid the base, where half of your starting material will act as the base, but generally এখানটা একটা ট্রাইইথাইল অ্যামিন বা ইত্যাদি ইউজ করা হয়। তো এর যে এই যে প্রোটেকশনটা দিচ্ছে, সেটাতে বুঝতেই পারছো এখানে যেরকম নাইট্রোজেনের উপরে আর তুমি তার যে লোন পেয়ার সেটা লেস রিঅ্যাক্টিভ হয়ে গেছে বিকজ এটা টারশিয়ারি হয়ে গেছে, as well as you don't have any hydrogen here, so no deprotonation is possible. So that's also valid here. You don't have any hydrogens here. That's if you have started from a secondary amine, then there is no hydrogen here, so no deprotonation. But more importantly, this being a conjugative electron withdrawing group -I-R exerting group, this nitrogen lone pairs is less nucleophilic and therefore electrophile সাথে reaction will be unfavorable. For example, if you take aniline, then with HNO3 at any condition you get very poor yield of nitration product, and that too on a meta position, because HNO3 immediately protonates NH2, becomes NH3+, which becomes meta-directing. More importantly, HNO3 being an oxidizing agent, it oxidizes the electron-rich aromatic ring, and this thing is converted to some quinones or some stuff. So to prevent that thing from happening and to access the nitrated derivative at the para or ortho position, we could acetylate this NH2 to corresponding acetanilide, then nitrate with HNO3 acetic acid at low temperature, because this is highly activated compared to benzene, and not that activated that it undergoes oxidation, but the reaction temperature has to be kept low. Otherwise, if you increase the temperature, then oxidation may happen, hydrolysis may as well happen. So you nitrate at the 4' position or at the 2' position. Steric hindrance will ensure that the 4' compound is the major product. Then you separate it by crystallization or some chromatographic technique, and then you hydrolyze. The removal of this amide will require you to hydrolyze this amide linkage, and after workup you will get your 4-nitroamine. You can do the benzoyl protection, which is the NBZ protection or NCOPH protection, the Schotten-Baumann reaction that you have done. You can do this thing in presence of brine medium, in a brine medium, after working up with sodium bicarbonate, or you could just use the benzoyl chloride in triethylamine so that you have your benzoyl protection. But these things are very difficult to cleave. They are stable to a pH of 1 to 14. So their hydrolysis is very difficult, very robust. Neither do they react with nucleophiles, or they don't react with organometallics except highly reactive organolithium. They do not undergo catalytic hydrogenation, and they prevent oxidation. So once you have put that, it sometimes becomes difficult to put it off. এটাকে যখন তুমি বসিয়ে দিয়েছো তারপর এটাকে ডিপ্রোটেকশন করাটা অনেক সময় প্রবলেম হতে পারে। সেই জন্য জেনারেলি বেঞ্জয়েল প্রোটেকশনের থেকে অ্যাসিডাইল প্রোটেকশনটাকে বেশি ফেভার করে। সেটা আমরা দেখলাম যে acidic hydrolysis followed by workup with alkali will give you the free amine. H3O plus hydrolysis will give you actually the ammonium salt, from which you can liberate the amine by treating this thing with the alkali. Next up is something called the carbamates, which are, you can think of, they are esters of carbamic acid. এইখানটা যদি হাইড্রোজেন থাকতো তাহলে সেটা হতো কার্বামিক অ্যাসিড বা কার্বামিক অ্যাসিডের ডেরিভেটিভ, এটা তার এস্টার। Treatment of primary or secondary amines with methyl as R is equal to Me or ethyl R is equal to Et, chloroformate in the presence of a tertiary amine or potassium carbonate that can act as a base will give you the corresponding methyl or ethyl carbamates. These are also known as urethanes. যদিও সেই টার্মিনোলজিটা এখন অর্গানিক কেমিস্ট্রিতে খানিকটা obsolete হয়ে এসেছে, we call them carbamates. These protected amines, they are like, they are on one side they are esters, on one side they are amines, so therefore they no longer act as nucleophiles. They are stable to oxidizing agents and aqueous bases, but they may undergo reduction when exposed to reducing agent, strong reducing agent. এদের তিনটে জিনিস আছে যেটা আমাকে এখানে পড়তে হবে, এবং এইখানে যতটা না লাগবে তার থেকে বেশি লাগবে আমার এটা সেমিস্টার পরের সেমিস্টারে, সেমিস্টার 5-এ যখন আমরা অ্যামিনো অ্যাসিডস এবং পেপটাইডস পড়ব। সো ফার্স্ট যে প্রোটেক্টিং গ্রুপ সেটা হচ্ছে বেনজাইল oxy carbonyl group, which is abbreviated as simply Z or CBZ. It is one of the most important nitrogen protecting groups used in organic synthesis, especially in peptide synthesis, as I have told you. It is introduced by reacting the amine with corresponding benzyl oxycarbonyl chloride in presence of a tertiary amine. This one is fairly resistant to hydrolysis or any kind of hydrolytic overtures, both in aqueous base as well as aqueous acid. So note the name, this is the benzyl group followed by a oxygen and followed by a carbonyl. So that is why people call it benzyl oxycarbonyl or CBZ or simply Z. The benzyl oxycarbonyl chloride is prepared by reacting phosgene with benzyl alcohol in toluene solution or in neat liquid phosgene solution in benzyl alcohol. You can get the corresponding benzyl oxycarbonyl chloride, which will react with the amine and offer the CBZ protection. The second carbamate of our series is the tertiary butyl oxycarbonyl or tertiary butoxycarbonyl, which is sometimes known as TBOC, but also known as BOC. That is another fairly widely used protecting group for primary and secondary amine. This is resistant to hydrogenolysis, and this also resists bases or nucleophilic reagents. However, being a tertiary butyl ester, it is cleaved under acidic condition. The BOC protecting group is installed when you react the amine with the corresponding tertiary butyl dicarbonate, or you could use BOC anhydride, just as I have used here, BOC2O, in aqueous or organic solvent in presence of a base, and also you have the formation of the tertiary butanol and carbon dioxide in this reaction medium. The third in this series and the final one is the carbamate, which is based on a rather unusual looking molecule known as 9-fluoroanyl methoxycarbonyl or FMOC. People also call it 9-fluoroanyl methyloxycarbonyl. Both names are interchangeably used. Now, despite this fluoroanyl, there is no fluorine here. Note very carefully that there is no fluorine here. It is this group which is known as the fluorine. When you studied your acid-base chemistry and organic chemistry, I perhaps have taught you this, and perhaps you recall that we talked about, the acidity of fluorine, indene, and toluene, and triphenyl, methane, etc., etc. So this group is fluoronyl. This is the 9 position, and you have a methyl followed by a oxy followed by a carbonyl. So you have this whole thing 9 fluoronyl methyl oxycarbonyl FMOC. How do you put it on? Corresponding chloride reacts with amine in presence of a pyridine base to give you the FMOC protected amine. Deprotection, how can you do that? This deprotection condition is very different from the two that you have already seen. For CBZ, hydrogenolysis. For BOC, it is the acidic hydrolysis. And for this one, you treat the molecule with piperidine or morpholine in presence of dimethyl formamide. So you get your deprotection via hydrogenolysis. This CBZ protection is removed by hydrogenolysis, but this one is generally resistant to acid or base. The tertiary butyl oxycarbonyl TBOC or BOC protection can be removed by acidic hydrolysis, but they are not susceptible to hydrogenolysis, or neither are they susceptible to acid. The FMOC protecting group is susceptible to basic hydrolysis, but that resists hydrogen catalyst. That means hydrogenolysis is resisted, and they also resist acid hydrolysis. So these 3 protecting groups are complementary with respect to each other. If you have in your molecule a TBOC protection as well as a CBZ protection, you can knock any one of them out selectively by choosing carefully the reaction condition. Similar is the thing when you have a TBOC and a FMOC, or a FMOC and a CBZ, etc. Or you could have all 3 protecting groups present in your compound, and then you choose to knock out one of them. If you use basic medium, then this FMOC will be knocked out. If you use hydrogenolysis, then this CBZ will be knocked out, and if you treat that thing with acid, then this TBOC will be knocked out. So these are called orthogonal protecting groups. Just like orthogonal orbitals do not overlap with each other, as we have known for a very long time, these protecting groups, they can be removed under specific conditions under which the other 2 protecting groups are not removed. So they are, in that sense, orthogonal protecting groups. So how do they get removed? If you use hydrogen palladium, then it is actually the toluene which is generated in the reaction medium. This is a free radical reaction which gives you a carbamic acid derivative, and this carbamic acid derivative will undergo decarboxylation. As happens with carbamic acid derivatives, they are prone to decarboxylation, entropy driven reaction, and your amine is released. For a BOC protection, you have the AAL1 cleavage giving rise to a relatively stable tertiary carbocation, which eventually goes over to an alkene and releases the carbamic acid derivative in the reaction medium, which follows the decarboxylation course to afford the corresponding amine. For the FMOC, the pKa of this hydrogen is around about 24. And that is because if you abstract this hydrogen, this is a conjugate base which is aromatic in nature. Here you have 6 plus 6, 12 plus 2, 14 electrons relocalized over this fluoronyl system. So it is aromatic, and then it ejects this carbamate ion, gives you alkene, and this carbamate abstracts the proton from this piperidine conjugate acid, gives rise to decarboxylation product, the amine and the carbon dioxide. So this in BOC and in FMOC, these protections are like elimination reactions. As far as this thing is concerned, this is an elimination reaction. As far as this part is concerned, this is also an elimination reaction. So obviously there are 3 types of elimination reactions. You may want to think what type of elimination reactions these are. Finally, we have the carboxylic acid protecting group. Carboxylic acids have definitely the most problematic situation is that you have this hydrogen being present here. That's acidic. The pK value is round about 4, 5, and if you have a strong base or organometallic compound, then this will be deprotonated. Again, if this does not create a problem and if you have lots of these, then you can allow for this reaction to occur, not protect this one at all, but this generally is not the case. Carboxyl protection is generally required. Protection is also required for enolization, because if you have carboxylate here, and this alpha hydrogen is less acidic, but for a very strong base it can give rise to dianions, carboxylate enolates. So that may also become necessary. The most common protection or the most intuitive protection is to convert this thing into an amide or a ester. So if you don't have a hydrogen here, then the deprotonation reaction cannot happen. However, the amides or esters, they are by themselves susceptible to nucleophilic attack if the nucleophile is strong enough, as well as esters, as you know from phase condensation, they very easily form enolates. So that protection is not there. So a complete protection where this hydrogen will also be removed and this carbonyl will be protected in such a way that the nucleophilic addition will not take place and also the enolization will not happen, that is offered by orthoesters. But those are kind of are intricate reactions which are not very applicable at your level. At your level, the protection of ester and amide is sufficient. We have talked about this orthoester protection, but that is only a cursory glance. We will not delve into any details of those reactions because that is not appropriate at this level. Ester formation, you can do that with many different techniques, out of which the first four you should be familiar with. The most common is the Fischer esterification, where you reflux a carboxylic acid with excess alcohol in presence of acid catalyst, or you could transform this carboxylic acid into acid chloride via treatment with SOCl2. Then you treat it with alcohol and triethylamine. The third one is you treat that thing with sodium hydride, you abstract this acidic proton, and then you treat it with a corresponding RI, which is basically asking the carboxylate to do a SN2 reaction on this alkyl iodide, which will mean that this R group has to be primary only. And from your discussion in diazomethane, methyl esters from carboxylic acids can be very easily obtained by treating this thing with CH2N2, where first a protonation happens, makes it CH3N2, and then ISN2 reaction from this carboxylate, which is by the way a weak nucleophile, but CH3N2 is a super electrophile, so the methyl group will be installed on the oxygen. The next two, the fifth and the sixth one, you don't know. But these are so important that I have given you a couple of examples. For all sorts of alcohols, you could use dicyclohexyl carbodiamide activated carboxylic acid in presence of dimethyl aminopyridine. That's a Stiglitz esterification. And the other one is stereochemically very important. That's a Mitsunobu reaction. Let us take a look at these two reactions. Here you have a ketocarboxylic acid which is being protected at the carboxylic acid level. You can protect this carbonyl in form of acetal. You can also protect this carboxylic acid by esterification, where the esterification is carried out in presence of dicyclohexyl carbodiamide, because esterification will require removal of water from this alcohol and the carboxylic acid, and this DCC acts as a water capturer. As you can see, this nitrogen, they have captured the two hydrogens of water, and this carbon has captured the oxygen that is derived from water. This is dicyclohexyl urea DCU. So that's a Stiglitz esterification, where you have esterified this thing successfully using a sterically hindered secondary alcohol, 2-propanol. The more interesting is perhaps the Mitsunobu reaction, where you are removing this hydrogen and that OH. The alcohol is losing the OH. Generally, that does not happen. What happens is this OH groups is removed from here, and this alcohol loses only one hydrogen. But I have tried to show you that it is not that case by highlighting this hydrogen and this OH in blue color. You are adding triphenyl phosphine and also a diethyl as a dicarboxylate, which is a kind of an amusing acronym, DATE, and the reaction is done in acetonitrile solvent. So PH3P is taking away this oxygen, becoming triphenyl phosphine oxide, and these two nitrogens are taking away the two hydrogens of the element of water that is being eliminated, and you have the alcohol combining with carboxylic acid, and that too with the inversion of configuration. You can see that there is an inversion of configuration. This directly tells you that there has to be breaking of this CO bond, otherwise the inversion of configuration would not have happened. যদি আমি এই chiral center এ কোথাও কোনো বন্ড না ভাঙি, তাহলে the only thing that I can expect is retention of configuration. And generally, if you use the Fischer esterification technique here, then it will be retention of configuration. However, in Mitsunobu reaction, that is completely opposite. You get inversion of configuration, and that is because the CO bond, the carbonyl carbon and oxygen, that bond is being broken in the reaction, somewhere in the reaction. These are multi-stage reactions which involve intricate detailed mechanism. We will not go into them, but these are examples which you may want to know because এরপরে অ্যাডভান্স কোর্সের ইন্টারভিউ ইত্যাদিতে তোমার এগুলো কখনো কখনো কাজে লেগে যেতে পারে। ইভেন ইফ ইউ ডোন্ট নো দ্য মেকানিজম, if you know what the outcome is, then that will help in creating a positive impression. অ্যালকিল এস্টার্স দিয়েই আমরা জেনারেলি প্রোটেকশনটা করি। সেখানে আমরা টারশিয়ারি বিউটাইল এস্টারের প্রোটেকশন দিতে পারি, সেটা জেনারেলি আইসোবিউটিলিন ইন প্রেজেন্স অফ কনসেন্ট্রেটেড সালফিউরিক অ্যাসিড আমরা দিয়ে থাকি। This becomes a very bulky group, and therefore this first of all this hydrogen is removed. Secondly, this nucleophilic attack from any highly reactive nucleophile, that is also discouraged by the presence of the bulky tertiary butyl group. The deprotection is very easily done with trifluoroacetic acid or etc. So that's a AAL1 mechanism where you have a protonation here and this becomes plus, and then you have the release of this relatively stable tertiary butyl carbocation, which will go to eventually the alkene, and your carboxylic acid will be released in the reaction medium. Or you can go for, if you have a methyl protection, then you can go for SN2 reaction using lithium iodide in polar aprotic solvents such as DMSO or DMF, where this methyl group has this carboxylate leaving group, iodide attacks, and this carboxylate leaves, aqueous acid workup will give you the corresponding carboxylic acid. Benzylic esters, they can be readily deprotected by hydrogenolysis. Toluene is a byproduct of this reaction, but that is not a problem. You get your carboxylic acid back, and that gives you a selective way of cleaving the benzyl ester, deprotecting benzyl esters, where you have other ester groups in the reaction medium that are not susceptible to benzyl hydrogenolysis like benzyl ester. Here the radical reaction can take place because you have the phenyl ring stabilizing the radical center here, just as we have seen for the amines etc. But the hydrogenolysis is not viable for either this one or that one. So if you have a methyl ester and a benzyl ester, you can remove the benzyl ester selectively, keeping the methyl ester intact by a hydrogenolysis reaction. That's a room temperature reaction, so that's very easily doable. Let us do an example here. This example we have already done in nitrogen chemistry, but let's do it again. They have asked you to synthesize glycine. If you think of glycine as a derivative of ammonia, that's a primary amine, then you can think of a Gabriel reaction, because Gabriel reactions are excellent as far as SN2 reactive electrophiles are concerned. So you take potassiothalamide and you take your alpha chloro acid. The alpha chloro acid can be very easily obtained from the corresponding acetic acid via Helvolat-Zelinsky reaction. So it's a Gabriel reaction, but the chloro acid cannot be used with potassiothalamide, because if you do that, it will just undergo acid-base reaction and you will not have your nucleophilic substitution. So this CO2H group is creating problem. You need to protect it, and protect it in the form of CO2ET. This CO2ET, this carbon is also electrophilic, but because this is a alpha chloroester, this carbon is highly susceptible to SN2, and you don't have to worry about nucleophilic addition at this ester. You have created this by Fischer esterification of the chloroacetic acid, and then you are doing this thing with the potassiothalamide, you have your N-alkylated thalamide, which is on hydrolysis. This one is cleaved. On hydrolysis, this one is also cleaved, and you get your two things at once. So deprotection is also unmasking the nitrogen as well as unmasking the CO2H. This reaction we have talked about before, and again this demonstrates the usefulness of simple ester protecting groups in creating or constructing this kind of molecules. But as I have told you, the other protecting groups are important for the carboxylic acid. One of them is the oxazolene. These are, yeah, as I know that they are beyond the scope of the syllabus, but these are so important protecting groups that I have to talk a little bit about them. 1,2,3-oxazolines, they are generally, they can protect the carbonyl group as well as the hydroxyl group of this carboxylic acid group. See, the OH needs protection, the carbonyl also needs protection from nucleophilic addition, and that can be done by this oxazolene, construction of this 1,3-oxazolene, which is done by 2-amino 2-methyl propanol, which is readily available. And this is protection which was done by Myers, A.I. Myers. He is one of the famous organic chemists who have done a lot of work on oxazolene protection. This oxazolene group protect this carboxylic acid from Grignard reagents, from lithium aluminum hydride. But when you add organolithium, these hydrogens are a little bit acidic, and organolithium being very highly basic, they will abstract these protons. So organolithium protection from organolithium cannot be offered, but otherwise it's a good protecting. You can remove this thing with dilute acid, H2O+. Again, not important for your syllabus, but for future courses maybe. And finally, we have the orthoester, the cyclic orthoester. One of the orthoester is being prepared by the fluoroglucitol. That's the completely reduced all-cis form of fluoroglucinol. Fluoroglucinol you met in your studies in tautomerism. Here you have fluoroglucitol. The fluoroglucitol reacting with carboxylic acid, giving rise to a trioxaadamantyl or TOA derivative. That's a tricyclic orthoester. This is like an adamantane, as you have perhaps recalled from your studies in melting point and boiling point, but only these 3 methylene units are replaced by this oxygen. So this is a cyclic orthoester. Or you could go for a trioxabicyclo 2,2,2-octane, which is obo protection, that is done by reacting with this oxytane derivative, where you have a primary alcohol. This coupling is done with DCC DMAP, that's a Stiglitz esterification reaction, and this ester is rearranged under Lewis acidic condition to give you the obo-protected carboxylic acid. So these mechanisms are very, very complicated, and therefore we don't go there. But the thing is that they offer a robust protection for carboxylic acid. They protect the OH, they protect the carbonyl. They are no longer susceptible to any sort of nucleophilic attack. That may come as a surprise to some of you who remember the organometallic chemistry, where organometallic reagents were reacting with orthoesters. So these orthoester protection, how come they are not reacting with Grignard reagents? These orthoester protections, they are not reacting with the Grignard reagents. No, they are very robust. That is because the cyclic orthoesters are much more stable and resistant to overtures of Grignard reagent compared to acyclic orthoester, and they are entirely compatible with Grignard reagent. You can do reactions on this part with Grignard reagent and still nothing will happen to these parts. So these cyclic orthoester, which are known as, which you can conceptually think as the esters, as the acetals of ester, they are very, very robust. We will give one example, but how do they, how are they deprotected? They are deprotected generally with acid hydrolysis followed by aqueous workup to release the carboxylate salt, which is again, treated with acid to give you the carboxylic acid. So maybe they have asked you to synthesize this compound. It is a long chain fatty acid kind of thing where you also have a carbonyl. So this thing will require you to cleave it somewhere around here to reveal a A3 synthone. That's a 1,3-dicarbonyl. That's a alpha beta unsaturated carbonyl. and you will need a nucleophilic center here. So you can think of a Grignard reagent reacting with reacting at this center. So that's a 1,4 addition that you need. So you need uh, a copper catalyst to carry out this reaction, or you could go for the Gilman reagent, but that is not necessary. If you do the organomagnesium reaction in presence of externally added copper catalyst, then it is the Gilman reagent or the Gilman cuprate or the organocopper. Uh, the regioselectivity follows those reactions. In this reaction medium, there will be formation of a RCU derivative, and that RCU will dutifully follow the 1,4 addition pattern. But to synthesize this Grignard reagent, it will be a problem. You can have a bromine here, but you cannot possibly add magnesium and hope that there will be a Grignard reagent here, because you have a carboxylic acid present in your reaction medium. You cannot possibly protect it via ester, because ester protection will not help you, because once you form the Grignard, the deprotonation is prevented, but the ester itself is electrophilic enough to be undergoing self-condensation with the Grignard reagent that you have prepared. So here you are forced to use the more robust protecting group that protects both the carbonyl and the OH of the carboxylic acid. That is, we have protected this thing with the TOA protecting group. Once you have done that, you can form the Grignard reagent here, add copper bromide so that your 1,4 addition is ensured. Then you add your uh, methyl vinyl ketone so that your conjugate addition takes place, and after everything you need to remove this TOA group, which you can do by aqueous sulfuric acid and aqueous chloride. So these are the ways in which the four functional groups, the alcohol, the amine, the carboxylic acid, and the carbonyl groups are protected. I have attempted to demonstrate with a few examples how the protection-deprotection strategy works. As I have told you, the protecting group strategy is a very important strategy for organic synthesis, and there are many functional groups and many other protecting groups that we could talk about, but our syllabus does not permit them. I hope that you have understood the concepts that I have attempted to illustrate here, and this concludes our discussions on organic synthesis, uh, because this is the part of the syllabus I have been assigned to. In the future, maybe if I am to teach other courses on organic synthesis, the selectivity, etc., then there will be video lectures on that. So I thank you for your patience, and I will be seeing you in the next semester.